So we are going to continue in our class with this thing. We have to see how the role of information and correlation in quantum mechanics. So we are basically interested in how how there is a exchange of information between the relative subsystem of that composite system, which we have been interested in. For example, if the operators are represented as they are Hermitian operators, normally we use in quantum mechanics, the operators are having property of being Hermitian. If Hermitian operators we are discussing these Hermitian operators A, B, and so on and so forth in relation to the state function psi. So these state functions are computed through formulas which have been which are prior to it. So for example, if there is an orthonormal basis, for example, phi I. Um, Leads to a square distribution, square amplitude distribution psi. So pi, or probability, it's given by the phi I psi square. Square. Or if you see it, we also represented it as like this, phi of psi. And we can define this information basis phi I for the state, for state psi with I of phi I psi simply as the information of this distribution related to the uniform measure. Now, I of phi of psi, if you want to write it in terms of how we define information measure, yes, n log n or p log p if it's probability. So we can have this pi log of pi. So the probability is given by this. We can have p of this log of p of square. So it's I phi of psi square ln of phi of psi whole square. So we can define now as an information operator. We can define as an information operator A for a state psi, where IA is the square amplitude of its eigenvalues. It's the square amplitude of the amplitude of eigenvalues. So now we can have both degenerate class as well as not degenerate class. For non-degenerate classes, the analysis may come out to be simple, which will say it will be a sort of a canonical way of looking at things, which has classical resemblance as compared to the non-degenerate states, where a given eigenbasis can have more than given eigenvalues. Which are corresponding to given eigenstates. So there can be more than a given eigenvalues for given eigenstates. But for degenerate, not degenerate basis, the mapping or the distribution will come out to be precise, such that if IA psi is pi of I, because if you remember in your understanding of quantum mechanics, more than one eigenvalue, different eigenstates may be operated upon by operators, giving a unique eigenvalue. But the operators acting on those eigenbases, they can be orthogonal or they can be orthonormal, or it's not necessarily there can be more than one eigenstates which are being operated can correspond to that unique eigenvalue. So it may be degenerate, or so if it's degenerate, so there can be more than one values, or if it's not degenerate, so there's a unique correspondence. So in that sense, if this is this, then you can, for non-degenerate states, we can define this information, this thing measure can be defined like this, where A is non-degenerate. For fixed psi, the information of all non-degenerate operators having same set of eigenstates is same. So now what we are going to do is, for example, for an information measure to get preserved, where the mapping is should be one-to-one or unique, you can have non-degenerate eigenvalues which will correspond to non-degenerate operators having the same set of eigenstates. So for that, with distinct eigenstates which will correspond to the same given eigenvalue, so the information IA can be written as sigma j phi ij psi log of log of this phi ij divided by mi. So in a sense you can say we are in a sense we can just what I should say, we can rehash or recover our how we defined refinement as a part of information measure. Means in a marginal distribution or in general, if two subsystems are relatively related, so we are only two random variables related in a given system which is composed of subsystems. The probabilities of two variables in two subsystems, it's independent of the other variables which may be there. So the same thing was talked of refinement. So it doesn't matter we are only in conditional probabilities, we are only interested in the operationally which variable is related with which variable, as compared to the other variables in that subsystems. They can be frozen or we are oblivious. So that property was seen as something called refinement. So we are going to use the idea of refinement here also for non-degenerate operators So we can use the same thing. So this can be said a non-degenerate operator, which can be constructed here, possesses, this is the inference, maximal information. Yes, it possesses maximal information. Yes, because the presence of other variables do not affect the information here on this the dependence. Now we can say it's convenient to introduce a new notion of projection operators. Convenient to introduce new notion of projection operators relevant to specified operator. So if we let A have eigenfunctions phi ij with distinct eigenvalues, so we can define projection operators for this eigenspaces with different eigenvalues of A, which can be defined as so to each projection there is an associated number mi and a multiplicity of generacy with the dimensions of I in that eigenspace. So we can say distribution of eigenvalues, distribution over eigenvalues of A for state psi Pi becomes sharply as Pi is P of lambda I, which is AI psi, where this is the expectation, where we are coming to our notion of information back, how we defined this information as n log of n or this log of n. So here this can be defined as it's defined as A of psi log of A of psi divided by m of I. So here to each projection operator defined by this multiplicity mi. So you can see it that where this mi comes. This is fine. So where this, so it's for each multiplicity, it's divided by the way we define them things in conditional probability. Now what we are going to see. So if we have now a subsystem which is defined, which we have again and again a system made up of S1 plus S2. So these can be two relative subsystems. So we have to see, we can just have whether conditional probability or conditional expectation or marginal expectation. Along with given distributions, we can calculate the probability distributions in these subsystems. So where S, which is S1 plus S2, may be a joint distribution. In that joint distribution, we have to see how whether we're going to go to have conditional or marginal distribution, how we can calculate them. So for uh, for 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 Pij is P lambda I mu j is basically first we are going to have what I should say. This is this fine. So for a pair of joint distributions S1 plus S2, we can have Pij. So we can which corresponds to two variables. Here this is Ai, Bj, psi of S. So it's two operators or two variables of this is the state psi. So now we can have a Pi. This is probability of one variable in terms of probability of joint distribution can be written as AI sigma of Bj psi of S. So you can have AI I square psi of S. This is for one variable. For other you can have Pij. Pi in terms of, so here we have, this is Bi, now we have sigma Ai, Bi operating on this side. So there is exchange of variables. So here it's I square. So since we have the property of projection operators operating on the same state, it will get I back. So the joint information is given by IAB is given by Pij log of Pij. Since there are two variables Mi and Ni, you can have Mi Nj. So you can again write it as Ij expectation of 2 Bj log of Ai Bj operating on state psi Mi Nj, sorry. So this is the information, joint information distribution, where Mi and Nj are multiplicities of eigenvalues lambda I and mu j. Now we can, the way we have a conditional distribution, we can, the marginal distribution information or marginal information can be, so we can have this and this. So we'll have IA can be sigma AI square psi of S log of psi of S. In the same way, IB can be written as log of So the correlation, finally the correlation AI is given by A, B, psi of S is given by the correlation of A and B is given by using this for again we'll have PIJ, probability of joint distribution can be log of PIJ and the variables are Pi, Pj. So this is the same formula, but here in terms of Pij. This is a probability distributions joint. This is the individual distributions Pi and Pj. So if you want to write it in terms of variables A and B, which may also be subsystems of S1 or S2, so you can write it as A and B log of, you can have log A of B, this is psi, log of A of B, psi of S. Here in the denominator it can be AI, IBJ, psi S. So which is where we know the expression does not involve the multiplicities as the information expressions. It doesn't involve multiplicity, so it means that a circle which reflects the independence of correlation in any information measure. Means whichever you measure, it doesn't matter whether this is first or this is second or this is prior or this is later. So this is in the language, it's also called something called canonical correlation. You might have heard the word canonical means in a sense classical. This means that there can be unique map between two variables or two operators or two states in that sense. Or it's a classical sense. Canonical is a so there is always a unique quantity, S2 with unique correlation. You can see it's better word, correlation, which has some fundamental unique correlation between subsystems S1 and S2. Two subsystems S1 and S2 of composite system S. So if we also said that these, what I should say, operators are Hermitian, if they are Hermitian, then the density matrix, which, if the density matrix is Hermitian, the representation is diagonal. So in particular, if we have a decomposition of two states, these subsystems, so if you want to relate, since we are relating two subsystems, relative subsystems, how we can relate parameters or probabilities or distributions. So of two these subsystems of this total system S. So if it's canonical, means if the operators are Hermitian, and then the diagonal things will contribute for a particular decomposition of psi, of S with state psi S. S1 and S2, we can choose a representation. We can choose a representation where a row 1 and row 2 are diagonal, where a row of S1, is independent of the basis of S1 and so on and so forth. So if we that representation is known as canonical. So we can have one subsystem even if it's Hermitian and the density matrix it's diagonal. So we can have a basis state which is independent of psi1 and vice versa. This means for a single, it's always possible to represent a single state psi of S by a single superposition, which means psi S can be written as AI, zeta I, neta I, where zeta I and neta I are orthonormal states of subsystems S1 and S2. It's how we can represent these relative subsystems and relate them with each other. So the diagonal basis space, it can be orthogonal or orthonormal. So if it's orthonormal, so you can have two representations which are done by A and this. That space can be written in terms of zetas and netas. Now we are going to see how we can see the inner product of these two orthonormal representations, zeta and neta. We have to calculate it and see things, what we get. So it's like we choose a basis, neta choose a basis neta I for S2, so that row of S2 is diagonal. First, for a single superposition, we have for a single superposition, psi S is this we have done. So this is this fine. So to construct this S2, row of S2 is diagonal, row of ij S2 is lambda I delta ij. So lambda I, if you remember, we have done it previously also. Lambda I lambda I, yes, pi is equivalent to lambda I ni. Yes. So here we are going to see in terms of this thing, where we can say let zeta ij zeta I be relative states in S1 for neta 1 in S2, such that zeta I is ni j phi j, neta I psi of S is phi j for any basis in phi of j. So now we can have you can have inner product of these two bases, psi I and psi j, psi k. So here, if you remember, we can write one of the states like this in terms of this state. Relative state of S1 for determined in S2. You can also have relative state of S2. This is S1 for determined in S2. We can have S2 for some other variable in S1. S1 vis-a-vis S2 and S2 vis-a-vis S1. And then we can compare the bases as a part of inner product. So in the same way, the way we have zeta I, we can also have zeta k can be similarly represented. Then we can also have nij. So here we have exchange of variables. Now we can also have zeta I, the inner product of these two. How we can see it? So it's basically this. In the first one, we can write ni here. It's sigma L phi L neta L psi of S star phi of M neta K psi of S phi of M. So this one you can also write it as phi of M neta K psi of S phi of M. This is any basis in phi of M. So you can have these two things, this and this, their inner product. But now we can, but here it's Ng. Ng. So now N and Ni, Nj, they will come together. So I just Nj star Ni Fl phi L neta J phi of S psi of S star phi of M neta K psi of S delta Lm. Nk, sorry. So you can have two normalization conditions. So now it depends. Nj, Nk, so it depends. You can have a delta function. It can be 1 or it can be 0. And that will give us the correspondence in that sense. So you can have sigma L. This is Nj star Nk. This is rho KL. Rho KL. This is basically this is phi L phi M and this is N. This is K L M. So you can say it's Nj. So it's Nj star Nk lambda K delta Kj is equivalent to 0 for J not equivalent to K. So since we are, so we suppose rho of S2 to be diagonal in this representation. So we have thus constructed a canonical representation. Canonical in the sense that for j not equivalent to 0, it's 0. For j is equivalent to k, it is 1 in that sense. So if it's 1, it can be 1-to-1 mapping between the variables of this state, substate with regard to the other substate. Yes. 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 So we can say that that rho of S1 is zeta 1 neta k psi of S star zeta k neta k psi of S. So it's basically zeta I neta k. So again, so we have to basically have a diagonal, the density matrix. This density matrix, rho of S1 is automatically diagonal by the choice of representation of bases in side 2. So the diagonal representation can be, if you want to represent it in terms of this as this product of this and this, of two states, it's like this and this. So we can have, now further we can write zeta I neta k as psi m, we can write it as am zeta m neta m star. Again we can have zeta j neta k al zeta l neta l. So we can have at the end with this. So at the end, if you just do it, it will be ai star ai delta ij is equal to pij delta ij, where pij is the marginal distribution over zeta I. So you can from this make an argument that there is a one-to-one correspondence. There is a one-to-one correspondence between. There is a one-to-one correspondence. So for A bar in S1 and B bar in S2. So if these are parameters in S1, one's relative subsystem and another subsystem, and here we can represent this basically rho as a k star if I or a k star is equivalent to delta kl, its probability is delta kl. So now if we have A1 in S and B in S2, you can say, and operators are in canonical representation, being perfectly correlated in the sense such that the joint square amplitude can be given by the joint square amplitude distribution of eigenvalues lambda I of A and mu g of B bar can be written as so we can have a so if it's lambda 1 of A mu g of B, these are two parameters which correspond to one subsystem, and this is for another subsystem. So we can say that they are perfectly correlated, and there is one-to-one correspondence between their eigenvalues. So we have come out argumentation which follows from this simple algebra, that how we can define the probability states for these two distributions which are composed of these relative to subsystems. And for particular degenerate cases, you can relate probabilities like this. And further, once you relate the two eigenstates or eigenvalues between this one subsystem and other systems subsystem, the mapping is one-to-one or unique as far as eigenvalues are concerned. And this can be seen as if we are basically correlating, correlation of operators, correlation of you can see as if there is correlation between operators A and B psi s. Now again we are going to use the older formula of n log n. So but here we are using these parameters A, B, which is given in a state psi. So P is this lambda and this mu, lambda and I and mu J. This is log of P of lambda and mu, lambda I and mu I, and here it's probability of lambda I and probability of mu I. Now, since it's not every, it's being factored on by this condition, delta condition. So we have P of delta ij log of P of I delta ij. This is Pi and Pj, you can see that. Or you can say it's a minus sigma Pi log of. So you can say we shall denote this quantity as S psi of S1 S2. Psi of S is called basically canonical correlation. Canonical in the sense that the subsystems S1 and S2 of the system psi of S, it's the correlation between pairs of non-degenerate system operators which define canonical representation. Now, where the density matrix are diagonal, then the canonical relations is given by so if it's diagonal, it's given by trace of if it's diagonal, it's because the off diagonal elements don't contribute, which we have defined from the given condition. So it's trace of and basically rho 1 S1 log of rho of S1 for subsystem, or because the mapping is unique, it's basically a trace of rho of S2 log of rho of S2. So which is which is invariant under unitary transformation. So you can say the entropy has a similar, it mimics the features similar to that of Boltzmann's entropy, or for a mixture where psi of S1 plus S2 is exactly mapped in terms of correlation of information for this S1, S2. So it's mapped by this thing, which is sort of, you can have defined it as canonical representation. And this is reminiscent of how variables are correlated or related in classical mechanics. So we have seen maybe how we can. So this is a relation up to this point, and we'll stop here and see how the formalism just will help us in some impending future, which is not too far, but we'll wait for some time. How can the things which we have learned here, how can what does it have to do in this, that the many world interpretation, how we can construct that state psi, which will explain things for us later, or which will explain for us how quantum state is to be construed. Stop here.